Yes, so we are back with another class, and today we are going to continue a little bit of hashing, and we are going to see hashing on strings. So today, once again, we are going to cover hashing, but we are looking at hashing specifically for strings. And there's one more thing that we are going to cover today, which is the RobinCarp algorithm, which is one way of hashing over a particular string. Right? This is for substring matching. Perfect. So let us begin. Let us start directly with a very simple question. The question goes something like this: that you have been given a string, let us say S. All right. Now you have to find whether it is possible to somehow permute or somehow rearrange the letters of the string B, somehow to permute or rearrange the letters of this given string so that it can be represented as a concatenations, a different, so that it can be represented as a different concatenations of some substring, of some string, basically. So let us take an example perhaps. Suppose that I have the string AABB, right? So currently, if I look at this string, is this particular string a concatenation? So let us suppose that A equals to 2. Can I somehow break this string down into two parts such that both these parts are equal after rearranging the string? Yes, I can. Right? So if I currently this is not currently this cannot be these partitions are not equal. But what I can do is I can perhaps rearrange it like this: A B A B. Right? This string is just a permutation of this previous string. And now if I see in this string, yes, there are two occurrences of the exact same string. Is that clear? So basically, you will be given a string like this, and you will be given a number such as 2, and you have to tell me if it is possible to rearrange this original string such that it becomes a concatenation of a similar strings. I hope the question is clear. Right? So what approach can we come up for this particular question? Let us always begin whenever we solve a problem. We always try to begin with the absolute brute force approach, because as we know, being able to solve a problem is always the first step. Right? Let us forget about the optimizations. Let us do the optimizations later. Let us first solve the problem. So what will the entire brute force look like? Well, we know that we have a string, let us suppose S, and let us suppose the length of string S is n. So we can try all permutations. So let us suppose that we have some permutation of the string S. We have some permutation of the string S, and we have the value of A. We have the value of A. Let us suppose A is 4. So we can check, we can split this string into 4 parts, and we can check whether this is equal to this, is equal to this, is equal to this. Simple enough. That will be the brute force approach. What will be the time complexity of this approach? Well, first of all, how many permutations, how many solutions do we have to check through? How many permutations can be there in the worst case? If the length of the string is n, then the number of permutations will be n factorial. All right, and given a particular permutation, we'll also have to check whether it satisfies this property. So that will take an extra order of n time per permutation. So the total time complexity will be order of n factorial times n, which is pretty bad, but at least we solved the question. Now, as most of you have already started pointing out, so Ashrita is asking to repeat the question. So let me quickly repeat the question once again. So the question goes something like this: that we have been given a string S. We have been given a string S, and we have been also given a number A. Right? Now we have to check whether it is possible to permute or rearrange this original string such that it can be represented as a different concatenations of the same string. For example, if I have this string AABB, then currently I cannot represent this as two different concatenations of the same string. Right? Suppose that A has been given as 2. However, if I rearrange this string into ABAB, now I can say that, okay, because A is 2, I can represent this string as two different concatenations of the same string AB. Right? That is the question. And the brute force approach that we saw, that simply involved trying all the different permutations and checking each permutation separately, which was pretty slow, but at least it will give us the right answer. Right? This is the brute force. Now let us talk about the optimized approach. And yes, so both Vaishnav and Parth have given the right approach over here. So has Akshat. Akshat has also given the right approach. Animesh, your approach is not quite correct. Right? So what the correct approach over here is, so what we can do over here is, we know that this string S, suppose that this string S can be represented. Suppose for now that it can be permuted and represented as A concatenations of the same string. Then what can we understand from that? What can we understand from that? Let us suppose we break this down into 8 different parts. Suppose we break this down into 8 different parts. After the permutation, we know that this particular substring has to be the same as this particular substring after the permutation, right? And so on. This also has to be the same as this, and this also has to be the same as this. So what do we know? Suppose a character comes over here, right? Suppose this character is A. So we know that this character must also be over here, must also be over here, and must also be over here. Right? Similarly, if there's a character B over here, this is how the permuted string should look like. Right? Suppose there's a A over here and X over here. So this is what the permuted string should look like. Yes or no? All right. So what can we basically say from this? We can see that whatever character comes, right, for any character, right, the frequency of that character or the number of times that character occurs in the original string, that has to be a multiple of A, right? It has to be a multiple of A. Why so? Because if it is not a multiple of A, then you will not be able to make A different copies of it. You have to make A different copies of that same character to repeat that string. So it has to be a multiple of it. The frequency has to be a multiple of it. So this is very simple now, right? This is very simple. All we have to do is we have to go through the string, and maintain a count of each character. Right? Count each character, right? And then check for each character. Check if the frequency is multiple of A. All right. So this we have to understand over here that this must go both ways, right? This implication must go both ways. So we have so far established that if S has the property, then every character occurs some constant times A times. Right? That is what we have established. But that is not sufficient, right? That is not sufficient. We have to establish that the other way is also possible. That if you have any such string, then you can always rearrange the string into A different subparts that match, right? And that is actually pretty simple to see. What we can do is once we have, let us suppose that we have several characters C1, C2, C3, C4, right? And all these characters occur in some constant, let us say alpha times A, right? This occurs beta times A, this occurs gamma times A, this occurs delta times A. Right? Now, what we can simply do is we can start putting these characters in, right? So we can put C1 alpha times. So this will be alpha times. Then we can put C2 beta times. Then we can put C3 gamma times, followed by C4 delta times. Right? So this particular thing will give us one part of the string, and then we can simply repeat this A times. And that will give us these frequencies that we so desire. Right? So we see that yes, this implication goes both ways. So this is both necessary and sufficient to solve our problem. Right? So the solution now becomes very simple. Just go through the string, count each character, and at the end we just have to check for every character if its frequency is a multiple of E. Perfect. Let us see some other approaches that we have. Sai is saying we first check if length of string is multiple of A or not. If it is, then we go with the solution, else returns false right away. Yes. So Sai has a very nice optimization over here. Sai says that, hey, if the original string S, let us say the length of S is suppose 10, and let us suppose that A has been given to you as suppose 4. Now we know that no matter what you do, no matter how you permute or what substring you choose, if you have a string of length n, you cannot make 4 substrings out of it of the same length. Right? You cannot make 4 substrings out of it of the same length. Why? Because simply 10 is not divisible by 4. Right? 10 mod 4 is not 0. Right? So this is one check that we can very well do. At the start itself, we can check if the length of the string is a multiple of the value A. Only then should we continue with the rest of the solution. Otherwise, we can very quickly return false. That's a nice optimization. Thank you, sir. Perfect. So I hope that you guys will be able to code it. Yes. So how do you count the frequency of a particular character? Well, this is easy if I know what the underlying character set is. If I know that my string consists of only lowercase a to lowercase z, then it is simple, right? I just have a frequency array of size 26, right? One for each character. But what if I do not know? What if I do not know what the underlying character set is? Then I can use something like a hash map. And that hash map will take care of figuring out the underlying character set for me. It doesn't really matter what characters I see. So what will be the time complexity of this optimized approach? Let us suppose that we are using a hash map. And let us suppose that the amortized time complexity of checking or insert in a hash map is order of 1 amortized. Right? Or basically, let's not say amortized, let's say expected. So what will be the overall time complexity? Well, now we are just iterating through the string and counting the characters, right? And finally checking if each of the values is a multiple of a or not. So this is very simple, order of n plus, so n is the length of substring plus order of delta, right? Delta is the size of character set. And we always know that size of character set has to be less than or equal to n, right? Because in the worst case, every character can be different. So I can just rewrite this as order of n. So that is the time complexity of the optimized approach. So what we see from here is that all these things are variants of hashing. Calculating a hash, so over here, our hash function was slightly different. Our hash function over here was just the frequency count of characters, right? And whenever we are solving problem related to hashing, we might have to choose our own hash function to make sure that it aligns with the problem that we are solving. So let us look at one more question perhaps. So suppose that we have been given an array. We have been given an array A of size n, and this array consists of n strings. So we have been given an array of n, and this array consists of n strings. We have to return the groups of all strings which are anagrams. Right? This is a very simple question again. So let us quickly understand the question. Suppose that I have an array that looks something like this. Right? So array is at, dog, god, right? Act, and fan. Suppose that this is my particular array. So over here in this array, if I rearrange the values, I can see that cat and act, they are anagrams. Right? So first of all, does everyone understand what an anagram is? Two words are anagrams. A and B are anagrams. Anagrams if and only if A can be rearranged to look like B. Right? For example, the words dog and the word God, they are both anagrams because there is one G, there's one O, there's one D. I can rearrange them to look the same. Right? Now the question is that we have been given an array and we have to return the groups of all anagrams. Okay, so over here, if this was given as the input, then our output will be what? So let us quickly number all these values. So suppose this is 1, this is 2, this is 3, this is 4, right? This is 5. So our output should be a list of lists. Right? Our output should be a list of lists. The first group is 1, 4. Right? 1 and 4, they are anagrams. The second group can be 2, 3 because they are anagrams as well. And in the last group, I have 5 separately because fan is not an anagram with any of the rest of the strings. All right? So given this as input, we have to give this as the output. Is the question clear? Perfect. So let us once again look at the brute force solution. Brute force solution. Right. In the brute force solution, what we can do is we can start with the first string. We can start with the first string, basically the A of 0, and we can compare it with the rest of the strings. A of 1, A of 2, A of 3, A of 4, A of 5, and so on. Right? We can check each string with each of the other strings. While checking this string, we have to check for anagram. How do we really check for anagram? Should we try all the possible permutations? Should we try all the possible permutations to check for an anagram? Not really, right? Is there any better way? So given two strings, we have to check if they are anagrams or not. Is there any good way of checking if two strings are anagrams or not? So suppose that we have been given a string A and a string B, and I have to check if A and B are anagrams. I mean, the brute force approach will be to check all permutations, and compare. Right? That is very, very bad. So what we can do is we can otherwise check the frequency of each character. Right? The frequencies have to match. And once again, if the frequencies match, then they are guaranteed to be anagrams. Right? Cool. We have another approach over here. So Ankush is saying that what we can do is we can simply add. We can simply add the ASCII values. Now this might not always give us the right answer. For example, suppose we have the following. Suppose that we have the following strings. So we have A and D, and we have B and C. Right? So we know that the ASCII values of this is 65 and 69, and this is 66 and 67. Okay, so this is 68. Right? These are the ASCII values of these. And if we see, then yes, 65 plus 68, this is actually equal to 66 plus 67. Right? So if we were to compare these two strings by the ASCII values, by the sum of the ASCII values, then we will the solution will tell us that yes, these are anagrams, whereas these are not anagrams. All right. So something like this, something like a simple addition, is going to leave us astray. It is not going to give us the right answer. In many cases, it will give us the right answer, but you can always come up with edge cases. Right? So the correct way over here would be to count the frequency of each character, because that does not lose any information. Right? That saves all the information. Is there any other way? So yes, this is definitely a way. A simpler approach could be just to sort the strings. Sort the strings individually. Right? So for example, if I have the string God and if I have the string dog, if I sort God, then what string will I get? I will get DGO. Similarly, if I sort dog, I will get DGO. And the sorting strings, they have to match character by character. If I have two strings, and if I sort both of them, then the sorted value should be the same for the strings to be analyzed. All right. So what we can do is we can compare the string A0 with each of the other strings and check if it is anagram. If it is anagram, we will put it in the same group. But we are still comparing every string. We are still comparing A of 0 with all the other strings, right? Simply we are comparing A of A1 with all the different strings. So the time complexity of this is perhaps not that great. What will be the time complexity of this brute force solution? It will be pretty high, right? So we have to compare every string with every other string. So that is order of n square already. And we also have to check the anagrams, right? Suppose that we are using sorting to check if they are anagrams. So that will be an additional, let us say, not n, let us say k log k, where k is the length of the string. K is the length of the string. So no. So Shiv Kumar says that we can rewrite this as nq. That is not correct, right? Because we cannot say that this is this is approximately nq, because the length of the string is n, is k. Right? The length of the array, that is n. The maximum length of the string, that is k. The length of the array, that is n. Now this has not been given to us in the question. But we simply cannot assume that each string is going to be the same length as the size of the array. Right? That is not correct. We have to keep these variables separate. So that was one approach. Now once again, we can do better. Right? We can do better by using hash maps. So how should we hash the values? What should the hash function be? Suppose that I have this string s, then what should the hash of s look like? What hash function would I like to come up with? So that automatically, if I do hash by chaining, then automatically I get my answer. Yes, so Animesh has the right idea over here. Animesh says that let us store the sorted string in the hash map. So basically, given a string s, the hash of s will be the sorted representation of s. So now things become very simple, right? So if I have, let's say, cat, dog, god, act, and fan, what I can do is I can look at the first string. And if I sort this, I will get ACT. Right? For ACT, I will store the string. I will store the value 1, right? So this is index 1, 2, 3, 4, 5. Okay? And suppose that these are the indexes are starting by 1. Right? So for act, I will store that, okay, this string is sorts to act. Next, I will move on to dog. So what is the sorted value of dog? That is DGO. So for DGO, I will store 2. Then I will come to God. The sorted value of God is also DGO. So for DGO, I will also store 3. Okay, then I'll come to act. So the sorted value of act is just act. So I will also store 4 over here. I will also store 4 over here. Finally, I will come to fan. The sorted value of fan is AFN. So for AFN, I will store 5. Right? And that will give us our correct answer. Do you guys agree? This is the final answer. So what we can do is we can sort each string and store it in a hash map, in a chain hash map. So this hash map stores. This hash map stores a string. So this is the key. The key is a string, and the value, corresponding value, is a list of indices, right? List of integers. Swapnil is saying, what if we take a map of size 26? It could be done in constant space. Well, Swapnil, you are assuming over here that the underlying character set is of 26 characters. Right? That might not be the case. It might be the case that the underlying character set has all the Unicode characters. Right? It could be Chinese, it could be Kanji, it could be Devanagari, all these different characters, right? Prakash over here says, instead of storing string directly, we can convert each character of each string into a range 0 to 25 as frequency. Yes, so Prakash over here says that instead of sorting the string, we can do an optimization there as well. Sorting a string of size k will take us order of k log k time. This will take us order of k log k time, but we can do better. Right? So if we will come to that. So if we look at the complexity of this thing right now, the complexity is how much? We have to go over each string, right, and hash it. How do we hash it? We sort the string, k log k. Right? So this is the current complexity. Now, Swapnil over here, not Swapnil, okay, Prakash over here says that we can also optimize this k log k part. Right? Instead of sorting, we can keep the frequencies itself. We can keep the frequency of character. Right? That is one other way of checking for anagrams. Right? The frequency should match. So in that case, our complexity will be reduced to an expected order of n times k time. And then what will our hash map look like? So our hash map will have to store what? So the key will be the frequency array. The frequency array of characters. So the key will itself be a hash map, basically. The key will itself be a hash map, or basically a frozen map. Hash map of frequencies, with character frequencies, and the corresponding value will once again be a list of indices. Right? Now, when you actually try to code this up, things might get a little difficult because using a hash map itself as a key can become tricky. Right? If you knew that okay, you had the character set of 26 characters only, then instead of storing the hash map of frequency, you could have just stored an array of 26 different values. You could have stored an array of just 26 different values, but you don't know what the underlying character set is. Right? So you will have to store a hash map, and hash maps are not usually hashable. So it is difficult to use hash map as keys. Perfect. Vignesh is asking, why are we seeing RobinCarp method over here? Well, Vignesh, RobinCarp method for string matching is just another very simple. I mean, it's not that difficult. It is just another hashing technique. And that is the next thing that we are going to come to. Perfect. Animesh says, what happens if the number of characters in a particular string is more than k log k? Well, Animesh, that is not possible. Right? So over here, k is the length of the largest string, of the longest string. Right? So if k is the length of the string, then it is not possible for the number of characters, in this string to be greater than k. Right? The number of characters has to be less than or equal to k. Yes, so Deepanshu over here is saying that if we go with this particular approach, if we go with this array approach, then the space complexity will be high. Exactly, Deepanshu. So suppose that our strings are Unicode strings. So how many different characters does Unicode have? Does anyone remember? How many different characters does Unicode have? Unicode has how many characters? It can support up to 65536 characters. Right? The number of characters in Unicode is huge. Right? So if we were to go with this array approach, if we were to store this array approach, then we will have to store an array of size 65536 for every string. That is very difficult. No, guys. ASCII has 256 characters. Unicode is much larger. Right? ASCII only has some English some English letters, some mathematical symbols, some accented letters, right, and some box string characters. But Unicode has a lot many letters. Okay, so this is not going to work, which is why we said that let us not keep an array. Instead, let us keep a hash map of the frequencies. But once again, if we are trying to keep the hash map, then things will get tricky because hash maps are generally not usable as keys. Vignesh is asking a very good question over here. Vignesh says, "Sir, I have a doubt. When we are doing competitive coding online, will the online judge also check the space complexity of our solution?" And yes, Vignesh, that is true. I mean, when you go to interview bit, when you go to Scalar Academy and interview bit, our online judge also checks the space complexity. Right? So we make sure that the memory that your particular program is using, the memory that is being used, we just monitor the memory that is being used. Right? And this memory has to be within a reasonable limit, depending on the programming language. So let us move on. I hope this solution is clear to everyone. Right? So the most optimized approach for this will be order of n times k. Right? If we do the Hashmap approach, so Hashmap of Hashmaps, it is not that simple. But otherwise, we can at least do it in order of n times k log k. Right? If we store a hash map of sorted strings. I hope that is clear. All right, now let us move on to the RobinCarp algorithm. So far, in both the questions that we have seen, we were trying to come up with our own hash function. We were trying to come up with our own hash function so that we could simplify our life. Right? We could simplify our life. Now, RobinCarp algorithm is another such algorithm. It is basically used for string searching. String searching. So let us quickly define what the string searching problem is. Right? So the string searching problem is very simple. You have been given a large string S. Right? This string could be, let us say, a book, or this string could be Wikipedia, the entire text of Wikipedia, or this string could be the entirety of internet, perhaps, or this string could be all the products on Amazon. Right? It could be any such thing, and you have been given a pattern. Let us say the pattern looks something like abracadabra. And you want to figure out, first of all, you want to figure out whether this pattern exists in my string. Right? That is one of the most important things that we do while we are searching. But more importantly, I need to find where exactly. Where exactly. So suppose that I have this string over here. I have a large string over here. And suppose my given pattern appears over here, appears over here, appears over here, appears over here. Then I should be returning the starting indices of all these different occurrences. That is what the string search problem means. Given a large string and a small search pattern, search for that pattern in the entire string and report all the occurrences of that string. We have to report all the occurrences of the string, not just one occurrence. So, what is the normal way? What is the usual, most trivial way that you can solve this particular problem? Suppose that I have a string S of size n and I have a pattern P of size m. Then how should I particularly go about searching for this pattern in the string? I can use some sort of a sliding window. Right? I can use some sort of a sliding window. So if I have this string, I can first check this particular thing for the pattern match. Then I can shift by one character and then check this particular string for the pattern match. Then once again, I can shift one character and search this string for the pattern match, and so on and so forth. Right? So I can keep a window of p size and I can slide it one character each. I can slide it right one character each. So how much time will this take? Well, let us look at the first window. So we are currently matching this particular portion of size. So we will have to verify each of these characters, right? That this matches this, this matches this, this matches this, and so on till the end of this. So each checks will take us order of p time. And how many checks do we have to perform? How many checks do we really have to perform? We have to start from this index 0 and we can go up till the index n minus p minus 1. Right? Because this last character will be at location n minus 1. So this is the last occurrence where the pattern p could occur. So it will be p times n minus p minus 1, which is simply order of n times p. Yes? No, this np is not that p versus np thing. Right? This np is not that. This np is just the string length of the strings. Now the question is, can we do better? Can we do better? So there are many string searching algorithms. Today we are going to discuss RobinCarp, but in the coming classes we will discuss more complex string searching algorithms. Right? So you can search string using tries, you can search string using automatas, you can search string using n different ways, and we will be covering most of them in the coming classes. But today we are going to talk about the RobinCarp algorithm. So the RobinCarp algorithm has one special insight. Right? The RobinCarp algorithm says that, all right, let us suppose that you have this particular string. Let us suppose that you have this particular string and you are matching for this particular pattern, P over here. Right? You will spend some time, you will spend P time to check if this is a match or not. Yes or no? You will spend P time to check if this is a match or not. Now, when you move this to one right, when you move this to one right, now once again you will spend P time to check if it is a match or not. Yes or no? That is what is going to happen. So can we improve this? Can we somehow reduce this time complexity? So what Robin said, what Robin and Carp said was that, all right, instead of comparing the strings, let me instead compare the hashes. Let me instead hash the strings. Let me hash the strings and let me compare the hashes. Right? So suppose that we have this particular part of the string, right? And we have this string that we are looking for, P. So if, let me call this string S dash, right? Let me call this substring S dash. So if the hash of S dash is not equal to the hash of P, right? If I have this hash of P, and if I looked at the hash of this, S dash, right? If I looked at the hash of this S dash, and the hashes do not match, then what can I say? Can this be equal to P? Can this substring match the same? Can this substring be the same as the pattern? No, it cannot be. Because if it is same as our pattern, then the hashes will have to match. So if the hashes do not match, then we are guaranteed that not a match. But if the hashes are equal, then what can we say? Can we say that yes, there are a match? Well, not really. Right? That depends on the hash function. Depends on the hash function. So basically, if the hash function is lossy, or basically if the hash can have collisions, then a matched hash means a match may be possible, right? A match might exist, right? It is not necessary for the match to exist because it could just be a simple hash collision. On the other hand, if the hash function is lossless, or that is, it is guaranteed to have zero collisions, then yes, a match is same as a match necessarily exists. So depending on our hash function, we know that yes, if there is a match, if the hash functions match, then an actual match might exist or might not exist. But we are at least sure that no matter what the hash function is, if the hashes do not match, then it is guaranteed that the substrings do not match. All right. So what can we do over here is, once we are trying to compare this particular substring for the pattern P, right? If we choose a hash function that has a certain property, so there's something called rolling hash functions. There's a certain property of a rolling hash function. The property is that once you have computed a hash of this thing, if you have to shift it by one character, then you can easily do it. You can easily calculate the hash of this thing in order of one time. Does that make sense? If you have the hash of P, the hash of, let's say, the index I all the way to I plus P, right? Then to compute the hash of I plus 1 all the way to I plus P plus 1, right? You can do this in just order of one time. Provided you have this previous hash. Right? Provided you have this previous hash. All right, but is this idea clear? That if we use a rolling hash function, then we can perhaps optimize our time complexity. Now let us have a quick look at one example of a rolling hash function. Right? So this is not the hash function used in RobinCarp. Right? Hash function. But this is one just example of a rolling hash function. Suppose that we simply add the ASCII values of the characters. First of all, as we saw that this particular hash function can have collisions, right? So this is not a perfect hash function. Yes, we just saw that what sort of collisions can happen. Suppose I have the string A and D and I have the string B and C, then the hash of AD will be equal to the hash of BC. Right? If my hash is just the sum of ASCII values, because this will be what? This will be 65 plus 16 or 68, and this will be 66 plus 67. Right? Both will have the same value. However, this is a rolling hash function. So suppose that I have this string. Let me call this A, B, C, D, E, F. G, right? I have the sum of these, right? So I have 65 plus 66 plus 67 all the way till some value, right? Let us say 72. Okay. Now if I have the hash of this, if I want to calculate the hash of this, perhaps some character over here. If I have to calculate the hash of this, then what should I do? Should I start once again from B? Should I start adding once again from B? I need not. I need not do that, right? Suppose this value was S. Suppose this value was S. Now I can just do S plus the code of alpha minus the code of A, right? I can just do this previous sum. I can add the code for this and I can subtract the code for this. And I can very simply calculate the hash function of this entire chunk. Yes, how much time will that take? That will take order of one time only. A rolling hash function is a function such that in which it is very simple to calculate the hash of the next substring once you have the hash of some substring. Yes, so Vignesh, yes, this is similar to sliding window sum. Right? This particular thing is similar to sliding window sum. However, this is not the hash function that RobinCarp will use. Right? This is not the hash function that RobinCarp will use. This is just an example of a rolling hash function. Right? So we will come to the decision of which hash function to use later on. We will come to the decision of which hash function to use later on. Let us first see that once we have this, what will be the time complexity of our total overall algorithm? What will be the time complexity? So I have this large string S of size n, right? And I have some pattern P of size n. So what I am doing is I am hashing. So first of all, I will calculate hash of P. How much time will that take? That will take me order of m time. Yes, because I have to calculate the hash of P. That will require going through each of the characters. Now I will start matching from here to here. Right? I will start matching from here to here. I will calculate the hash of this thing. I will calculate the hash of these things and I will check if the hashes match or not. If the hashes do not match, if hash does not match, then what will I do? I will slide right. I will slide my window to the right. And how will I slide my window to the right? To calculate the hash again, I will remove the value of this thing. And I will add the value of this thing. Right? And that will allow me to recompute the hash of this particular substring. Yes? So recomputing the hash will take me order of one time. So sliding right will take me just order of one time. Right? If the hashes do not match. But if the hashes match, if hashes, basically else, now what can I say? If the hashes match, as we just saw, that depending on the hash function, it is not guaranteed that the pattern exists, right? Because it could just have been a collision. It could just have been a spurious match. In that case, what do I do? In that case, I have to verify if my match is correct or not. So else verify. How do I verify? Verification is very simple, right? I look at the first character, second character. I check if all these characters match. Suppose my hash was same. Just to confirm that the string is actually the same, I can compare it letter by letter. So verification takes me order of m time, where m is the length of my pattern. Perfect. And so this is part of the inner loop. This is code of the loop. And how many times are we repeating this? We are doing this for every window. Right? We are doing this for every window. And how many windows are there? There are order of n windows. Right? There are order of n windows. So basically what will happen is our time complexity will look something like this. If hashes do not match, so basically if there are no collisions, then what will happen? If there are no collisions, then every match is a guaranteed match. Right? Every particular match is guaranteed to be correct. Right? On the other hand, if there are collisions, if there are a lot of collisions, then every match, most of the matches will be spurious. Right? Most of the matches will be spurious. So can someone tell me what will be the worst case and best cases of this algorithm? So if there are no collisions, what will be the time complexity? Well, the time complexity will just be order of n. Right? The time complexity will just be order of n plus m, because if there are no collisions, then I'm guaranteed that as soon as the hash functions match, I'm guaranteed that the pattern exists. I don't have to verify it. If the collision possibility was not there, then this verification step is unnecessary. I don't really have to do that, because every hash function match is guaranteed to be a pattern match. But if there is a chance of collision, then I have to do verification again and again and again. I have to keep doing verification. So in the worst case, as we see from this loop, this loop can go order of n times order of m. Right? So the total time complexity over here can be order of n times m. Right? And this time complexity, as we see, this is no better. This is no better than the brute force. If you look at the brute force solution, then the brute force solution was just order of m times n times p, right? So it is no better. RobinCarp is no better if the hash function has a lot of collisions. So the entire functionality of RobinCarp, the practical performance of RobinCarp will be based on whether you choose a good hash function for your use case or not. Right? So RobinCarp basically best case with perfect hash. This will take us order of n plus m time. Right? But in the worst case with imperfect hash will take us order of n times m time. Right? Now the question arises, what hash function should we use? Right? So can someone come up with a nice idea of a hash function? Well, we would want the hash function, to be as lossless as possible. We want to retain as much information about the string as possible. For example, if we have the string ABCD, if we add the ASCII values, are we retaining a lot of information? We are not necessarily retaining a lot of information, right? Because the hash of this is the same as the hash of DCBA. Right? So we are not retaining a lot of information. So this is a very lossy hash function. What will be the perfect hash function? What will be the completely lossless hash function? Well, I can encode each string into an integer. Right? I can actually encode each string into an integer, right? Because every string, when we look at it, every string is just stored as bits and bytes in the memory. Right? Everything in the computer is just zeros and ones. So I already know some way of encoding a string into an integer. Right? But if we are not sure how to encode the string into an integer, I can manually do it. Right? Suppose that my character set was ASCII. ASCII can have 256 different values. Right? ASCII can have 256 different values. So I can just treat this as a number in base 256. Right? I can just treat this as a number in base 256 and convert that number into base 10. What is this number equal to? So what is D? D is 97 plus 4. Right? That is D. So this is 101. The ASCII code of small d is 101 times 256 to the power 0. Plus, what is C? It is 100 times 256 to the power 1. Plus B is 99 times 250. Okay. I guess I messed up. This is 100, this is 99. This is 98 times 256 to the power 2 plus 97 times 256 to the power 3. Yes or no? This is how I can make sure that I have the entire information of the string. If I have this hash function, then it is guaranteed that there are no collisions. Right? Because I'm not losing any information. I'm just encoding that string. I can go from here to here and I can go back. Right? So there's no loss of information. But would this hash function usually work? Is it possible practically to use a hash function like this? Not really. Because these hashes can get arbitrarily large. Right? Suppose that my pattern is of size 50. Right? My pattern has size 50. Right? So in my pattern, this character, the ASCII value of this character will be multiplied by 256 to the power 50. That is ridiculous, right? That is a huge number. So I cannot possibly store this in a 64-bit integer or even a 128-bit integer. Right? That is not possible. So I have to reduce the size of the hash. Right? I have to reduce the size of the hash. And one common way of doing that is to just take a mod. Right? Mod or modulus. Yes. What should we usually take a mod by? Well, we can try to take a modulus by the size of our hash. Right? Suppose our hash, we can store 64-bit integers as hash. Then we can simply mod it by 2 to the power 64 minus 1. Alright, we can simply mod it by 2 to the power 64 minus 1. Alright, usually it is still a better idea to use a large prime number for modding, right? Because if you use a prime number, it has a slightly better distribution for the hashes. Perfect. So RobinCarp says this. RobinCarp just says this, that given a particular string, if you are trying to find a pattern, first of all, find the hash of the pattern. Right? And this is the hash. Hash is just the encoding of the pattern. Hash is just the binary encoding of this pattern, right? with some modulus n, right, with some large prime number p. Is that clear? Once you have calculated this hash, then compare the hash of each substring. Compare the hash of each substring with this hash. If it is not a match, then simply slide the window to the right. If it is a match, then please go and verify. Right? Please go and verify. Now, is this particular hash function rolling hash function? Suppose that you have the hash value of this, right? Say you have A, B, C, D, right? And let us say that the character set is suppose 256, right? So this is 256 to the power 0, D times plus. So let me just rewrite this. This is just D times 256 to the power 0 plus C times 256 to the power 1 plus B times 256 to the power 2 plus A times 256 to the power 3, right? Where A equals to 97, B equals to 98, C equals to 99, and D equals to 100. So this will be my actual encoding, and I will also mod this with some value. Let us say M. Okay, this is the RobinCarp hash function. Is this a rolling hash function? Basically, if I add a new character over here, E, suppose 101, then can I calculate the hash of this part? Can I efficiently calculate the part of hash of this part? Well, yes, I can. Let us quickly see how. So what is the hash of this part? Right? Let us first write what the hash of this part is. The hash of this part is this: B times 256 to the power 3 plus C times 256 to the power 2 plus D times 256 to the power 1 plus E times 256 to the power 0. This is the hash of this BCDE. All right, let us see if we can convert this, if we can somehow get this value from this value. All right, so first of all, what we will need to do is we will need to subtract the value of this. So what we can do is, first of all, from this we can subtract A times 256 to the power 3. Now whatever remains, so what part will remain? This part will remain. Right? This part will remain. But we see that this part has one less part. Right? So currently B is being multiplied by 256 square. We need B as 256 to the power 3. Similarly, D has been multiplied by 256 to the power 0. But we need D multiplied by 256 to the power 1. So we just multiply the remaining thing. With the base 256. Right? And then we just add this last value. Then we just add this E times 256 to the power 0. That is going to give us the new hash function. Right? This is the same as binary. Right? If you have this binary number, and you know the base 10 representation of it, or if you have the base 10 representation of it, then you can remove this and add something over here, right, to get a new particular value. That is perfectly valid. You can totally do that, right? So this is what the RobinCarp hash function is. And yes, this is a rolling hash function. Right? Now, there's one catch that you have to understand over here, that because this is a modulus, this is going to work, right? Basically, do you guys know that modulus distributes over addition equals to A mod M plus B mod M? Right? So notice that there is some loss of information happening over here. Right? Once you have calculated this, after that you are losing some information because of this mod. Right? But that doesn't really matter, because modulus distributes over addition. It also distributes over subtraction. So notice that we have to subtract this value, but we can do that because we are using mod. Similarly, we have to multiply this value, and modulus also distributes over multiplication. The only reason we can do this is because we are using the modulus operator. We are losing information in a manner that mathematically makes sense. If we had lost information in some other manner, we would not have been able to reconstruct it. Right? We would not have been able to have the rolling hash property. Perfect. So this is basically it. This is the RobinCarp algorithm. So this was just some string matching using the hashes. Perfect. Surit says, are we not going to do a modulus on the next window? Yes, Surit, we are going to take a modulus on the next window as well. Right? So after we have done this, so basically, we have the hash. Of previous window. Right? Let me call this H. So what we are essentially doing is we are saying H minus what was the first character, right? Character 0 times base to the power the length of P. right? Base to the power length of p. So we will subtract this. Then we will multiply the result with the base. Right? Then we will add what? We will add the new character. Character, let's say, call this new. And let's call this character O. We'll add new character, and then we will once again take the mod with the same value m. Length minus 1. Yes, my bad. Length minus 1. Thank you for that, Rajiv.
Okay, so guys, till now we have studied what is hashing. We have also studied an algorithm for string matching using hashing, right? Okay. Now, when we talk about strings, there is a vast majority of problems based on strings which can be solved using hashing. Okay, so Hashmap is a very powerful tool when it comes to solving problems of strings. Okay, so we are going to study a few problems today. We will be solving some problems based on strings which can be solved using hashing, and we will also be solving a problem which will involve some other techniques. But majority of the problems can be solved using hashing. Okay, so let us start the class with a very easy type of a problem. Let us say that you are given a string. Okay, let's say that this string is interview bit. Okay, you have to find what is the first non-repeating character. Okay, first non-repeating character means in the given string some characters might be repeating, some might not be repeating. So which is the character, which is the first character which is non-repeating? Okay, so in this case we can see that I is a character which is repeating in this string, so this is definitely not going to be an answer, right? N is actually the first non-repeating character because there is no n after this n, right? So n becomes the answer for this case. Okay. Let us take another string. For example, let us say scalar academy free classes. If this is the string, what should be the answer? If this is the string, we can see that s is repeating multiple times in this string, so s cannot be the answer. C is also repeating, C also cannot be the answer. A is also repeating, L is also repeating. Okay, E is also repeating. R is also repeating. Okay, D is the answer, right? So in this case, D becomes the answer. Okay, Scalar Academy free classes. D is the first non-repeating character in this string. Okay, so we'll quickly discuss the solution. Okay, there are no white space. Okay, you can assume that there are no white space in this string. Okay, this string has no white space. Okay, so what is the minimum information that we need to return this answer? The minimum information that we need is, first is that I want, so I will just write what is the info needed. Okay, first thing is, since I want to find first non-repeating character. Non-repeating character means a character which is occurring exactly one time, right? A character which is present in this string exactly one time. So the first information that I need is what is the count of all the characters in the string, right? So what is the frequency of each character? Because only if I have the frequency of each character, then only I can comment whether the characters are coming one time or multiple times, right? So this is the basic info which is required. The second basic info is, since I also want the first non-repeating character, so this information will give me which all characters are repeating, which all are non-repeating. If for solving this problem, I also want which is the first such character. So I will also have to check the order, right? The order of character in which they are appearing in this string, right? So now, how can I compute the frequency of each character? Is there a very easy way to do that? Right, you can use a hash map, right? Or you can even use an array of size 26. That will also suffice, right? You can use an array or maybe a hash map for each and every character. If you are using an array, index 0 will correspond to the frequency of character A, index 1 correspond to the frequency of array B. So if this is a string of only let's say small case characters, then you can use an array of size 25. If you are including each and every character, then you can use an array of size 256. Or what you can do is you can have a hash map. Both of them are same thing. So a hash map of character and integer. Okay, this will also suffice. Now, once you have a hash map or maybe a map array, what you can do is you can iterate over this array, iterate over this string, and you can count the frequency of each and every character, right? So let us say that A, B, C, A, C, B, D, E. If let's say this is the string that we have, okay. Now, if I am if I want to build a hash map, after I iterate over this array and keep the count of frequency of each and every character, I will have something like this, right? A, B, C, D, E. All the unique characters will become the key, and corresponding to each and every unique character, we'll be having a count. Right? So against A, we'll be having 2. Against B, we'll be having again 2. C is also 2. Let us also have F and G. Okay. Then and another C. Okay, so C, count of C will be 3. Count of D is going to be exactly once. Count of E is 2 for F1 and G1. Right. So now we have got the frequencies of each and every character. Okay. Now, what is the second information which is needed? The order of the characters, right? So now after building this array, we know that these are the characters which are appearing exactly one time in this string, but we want to return the first such character. So how can we return the first such character? We need the order. Do we have the order already? Yes, right? We already have the order stored in this string. So again, we can iterate over this string and we can check for each and every character, right? So if you again iterate over this string, you can check character wise character whether this character is a character with single occurrence. No. So A is removed. Then you go to B. B is also not occurring exactly one time. C is also not occurring exactly one time. A again is not occurring. C can be skipped. B can be skipped. Then when you come to D, you see that D is such a character which is occurring exactly one time, and this is the first character that we have seen till now while iterating the string from left to right, right? So D becomes the answer. Okay, so how are we going to solve the problem? First we build the frequency array, or first we build the frequency hash map, and then again we iterate over this string, and character by character we check whether this character is a single occurring character or multiple times occurring character. If it is a single occurring character, we just return this. Okay, now some of you are suggesting that taking XOR can solve the problem. No, taking XOR cannot solve the problem because it is not guaranteed that all the other characters are occurring even number of times, right? So XOR is not going to cancel each and everything. In this case, if you can just take what is the XOR of this, so A and A will cancel out, B and B will cancel out, right? E and E will cancel out, but then you will be left with the XOR of C, D, F, and G, and you don't get any useful information from here, right? So XOR is not going to solve this problem. Then second option that is proposed is, can we do it using sorting? Shubhadeep, if you sort the if you sort the characters, you lose the order, right? But you need the first non-repeating character first in this given string. So sorting again cannot solve this problem. You will have to solve this problem using this way only. Okay, is this clear to everyone? Okay, let us solve another very interesting problem. So now you guys should keep an eye on this thing, that how Hashmap is enabling you to solve this problem very easily, right? Okay, let's move on to the next problem. The next problem says that you are given two strings, okay, and you have to tell whether the strings are isomorphic or not. So you are given two strings, you have to check whether the strings are isomorphic or not. In the context of this question, the meaning of isomorphic is that if you replace each and every character of string A by each and every character of string of the second string, you get the same string. Okay, so right, so there has to be a symmetry between these two strings. For example, if I have a string add and another string egg, right? So now if I just replace A by E and D by G, I get the second string. Okay, there has to be a symmetry between them. By symmetry in this case, we mean that there has to be a one-to-one mapping between the characters. Okay, so can I say that ABC is isomorphic to X, Y, Z? Is this correct? Yes, this is correct, right? Because you can replace A by X, B by Y, and C by Z. This is absolutely correct. Okay. Let us take another example. If I say that I will have, let's say, ABB replaced by CAC. Is this correct? So in this case, I can replace A by C, then I can replace B by A, but to make it correct, I will have to replace B by C for the third character, right? But we already have a mapping for B, which is A. So I cannot have another mapping for B. So this is wrong. Okay. So now is the problem clear to everyone? You have to have a one-to-one mapping between the characters of string A to characters of string B. Two hash maps for each string and their character frequency. Okay, Azim, do you need the character frequency here? Map of character string with each other. Yes, Akshat, that will work. But do you need a one-way mapping or a two-way mapping? First, check if strings are of same length. Okay, if they are, use a hash map and check if it already there in the map. Sai Kiran, you are saying that you will build a map or character to character map, right? If that is the case, then it's correct. Can we take ASCII difference between two strings? Heyman, just take some examples and check if that is going to work. Dictionary with each character mapping. Okay, Vignesh, that is in the right direction, but will that solve the problem? Okay, now the most commonly sent approach that I can see is that take a hash map, which is a character to character hash map. And in this hash map, we'll be keeping a mapping of characters of string A to characters of string B, right? So the key is going to be the characters of string A, right? So let's say that if I am creating the map for these two strings, I will map A to C, then I map B to A, and every time when I'm adding an entry to the map, I always check whether that key is already present or not. So when I add the last mapping, which is B to C, I see that B is already having a mapping, so I can return false. You can directly have a mapping of characters of string A to characters of string B, and while entering the mapping or while inserting the mapping in the hash map, you can just check whether the key is already present or not. If the key is already present and if the mapping is different, then you can return false, right? I can see it's clear to most of you, but is it correct? Let's take an example. What if I have string A is AB, second string is AA, right? What should be the answer for this case? Should it be true? Should it be false? This should be false, right? Because I am having a mapping from A to A. And then since this A already has a mapping with A, it cannot have a mapping with B. So this should be false. But if we go by this approach, what we will do is we'll put a mapping A to A, and then the next mapping that we are going to put is B to A. We will check the key. Key is not present, right? A is a different key, B is a different key. So we will insert this mapping as well. And according to our approach, this is going to give a right answer, which is wrong. So what do we need to do? We need to see whether there exists a one-to-one mapping. What does one-to-one means in terms of functions? One-to-one means that if A is mapping to this character, A should have exactly one mapping on the right side, and this character should also have exactly one mapping on the other side. So what we'll have to do, we'll have to keep both the mappings, right? So one hash map is not enough. We'll have to have two maps to store both the mappings, right? So both directions should be stored. So what you will be doing is you will be storing A to A. Simultaneously, you will also be storing this reverse mapping. Then you enter B to A, and then the reverse mapping is A to B. Now here you will see that this key is already existing, so this is not possible. So both of them are important. Okay. Why do we require two hash maps? Because in a single hash map, to check whether A is a value of any other key or not, you will have to iterate over each and every key, right? That is why that is not optimal, and hence we can use two hash maps to store both directions of mappings. Okay, cool. So now I think you should be getting a feel of how to solve string problems using hash maps or maybe using arrays of constant size, right? What is the time complexity here? What is the time complexity of this problem? So we are iterating all the both the strings exactly once, right? And then we are putting in the map, and then we are checking in the map. So whenever you use a map, especially if you are using an unordered map in C, or if you are using a hash map, we assume that the average time complexity of insertion or lookup in the map is order 1, right? So going by this assumption, the time complexity of this problem is nothing but order n, where n is the string length, the minimum out of the two strings. Okay. Will we code these problems on some code editor? Shrestha, you can code, or like there is an assignment based on strings as well. You can also attempt that assignment. Some of these problems are there in the assignment. Okay. Okay, let's move on to the next problem. Will this logic work for ABB and BBA? Yes, Pratyusha, check it yourself. Will this work or not? You store a mapping from A. So what Pratyusha is asking, she is saying that there is a string ABB and then BBA. Okay. So you store a mapping from A to B. Simultaneously, you store another mapping from B to A. Right. Then you store a mapping from B to B in this map. And here again, you try to store the mapping from B to B, but you check that this key is already present with a different value. So this is going to fail. Okay. Okay, let's move on to the next problem. The next problem says that you are given a string and you have to remove pairs of duplicate characters placed together. Okay, you remove pairs of duplicate characters placed together. For example, what do we mean by this is, let's say that the string is A, B, C, C, D. So now we can see that this is a pair of duplicate characters and it is placed together, which means that these two duplicate characters are placed next to each other. So you have to remove them. So the output that you are going to get is going to be A, B, and D. Okay. Then the next example could be that A, B, C, C, B, D. Okay. Not D, D. It should be B, D. Okay. If this is the question, then first what you do is you remove these two. Okay. So let me add something extra here. You have to recursively remove. Okay, recursively remove pairs of duplicate characters, which means that here if you remove C and C, then the string that you get is A, B, B, D. Now even in this string, B and B forms a pair of duplicate characters. So you will have to remove this as well. So the final output is going to be AD. Okay. In some of the cases, it might be possible that you will have to return an empty string. For example, if you have A, B, C, C, B, A. In this case, the first removal will remove the two C's. So you get A, B, B, A. Then you get A, A, right? And then finally, you get a empty string. Okay, now we have a test case. What if the input is A, B, B, G. Okay, if this is the input, then in the first attempt you can either remove these two B or these two B. Okay, whichever pair you remove, you will be getting A, B, G. And now there is no duplicate character, right? No pair of duplicate characters. So this remains the answer. Okay. Okay, so one very commonly, or the first approach that comes to the mind is that you actually remove all these characters one by one, right? So what you will have to do is you first remove this pair, and then you get this intermittent output, and then again in this string you check whether there is a pair which is occurring together. Then you remove this, right? This is one of the approach, but I think this should be obvious to everyone that this is going to be very unoptimized approach, right? So what should be done? Now, if you notice in these example, let's say that we have A, B, C, C, B, D. Okay, if this is the case, right? So I check A and I check B. These two are not same, right? Then I check C. Again, B and C are not same, right? So what we can do is once we reach C and this C, correct? So now we can see that these two C's are same, correct? So now they have to be removed. But if you are removing this pair, there is a lot of chance that you will get another matching pair before and after these two C's, right? So if you get this pair, what you can do is you can maintain these pointers. So what is the character that you need to check on the left side? On the left side, you need to check the character which occurred just before this pair. On the right side, you need to check the character that occurred just after this pair, right? So you can just maintain 2 pointers and you can check this thing. And a very, very easy way to do the exact same thing is if you use a data structure that supports these operations very optimally. Do you guys know about such a data structure which can solve this type of a case very easily? You always, so if you are moving from left to right, you are always concerned about the last seen character, right? So if first you see A, then you see B, then you see C, then you see another C. Now you know that you have to remove these two. So these two can be removed, and then comes another B. So what is the character that you need to check? The character which was entered just before C. Okay. So now you remove these two, and then comes let's say you also have A, then comes A, right? So now you have to remove these two. So you always require the visibility of the character which was seen last, right? Or which was seen just before the character that you have removed. So stack is one such data structure that provides us this functionality, and it can be very easy to use. So what you can do is you can maintain a stack, right? And now whenever you get a character, you insert it in this stack. So you get let's say A, you insert it in the stack. Then you insert it in the stack if the stack is empty, right? Now if you get a new character, you first check it with the previously seen character. If these two are same, then you remove both of them. If these two are not same, then you enter this inside the character. So you will be pushing it. Okay. Now comes C. Again, you check whether this new character is same as the previously seen character. No. So you can again push C as well. Okay. Then comes another C. Now you can see that this C is same as the last pushed character. So you can pop this out and ignore this new C as well. So these two are removed. Now you get a B, right? So as we have seen, the concerned character is this B, which was last pushed in this stack before we pushed C, right? So now you check this B with the top of stack. You again see that these two are same. So you can remove this B as well. Then you get D. So now you can see that D is not same as the top of the stack. So you can insert it. Once the complete string is visited, whatever is remaining inside this stack is going to be the answer. What if it was A, B, C, C, D, B? After removing C while checking previous character and next. Okay, let's take the example proposed by Akash. Akash is asking what happens if we have A, B, C, C, D, B. First of all, what should be the answer in this case? The answer should be A remains as it is, B, D, B. This should be the answer, right? These two B will not be removed because they are not together, correct? So if you take a stack, first you enter A, then you get B, B is not same as A, so you enter, then you get C, C is also not same as B, so you push, then you get another C. Now these two C are same, so you pop this C. Then you get D, so you push D, then you get another B, you push B. But whatever is remaining is same as the answer. So it is going to work. Okay. Can we do through recursion? Yes, Ankit, you can do, but that is going to be unoptimal because after you remove one pair, you will again have to iterate over the complete string to check whether there are such pairs or not, right? How can we do it using maps? Okay, so guys, again, all the questions of strings cannot be solved using maps. There is a fixed set of pattern that you can use to where you can use map. For example, any problem where you see that frequency is being talked about, or you're being asked about what is the first occurrence or the last occurrence, right? All those types of problems can be solved using maps, but not all the problems can be solved using maps. So this cannot be solved using a map. A stack will be a better data structure to solve this problem. So let us solve one more problem before we end the class. So now this is a very, very interesting problem. The question says that you are given a string and you have to check if you can form this string, or you can construct this given string just by repeating a substring of this string. Okay, by repeating any substring of this string. For example, if the given string is ABC, ABC, ABC. Okay. Now, if this is the string, so first try to understand the problem. The problem says that you are given a string. You have to check that whether you can construct this given string just by repeating any substring of this string any number of times. For example, in this case, ABC is a repeating substring, right? So what you can do is you can just pick ABC and you can repeat ABC 3 times and then you get this complete string. Okay. Another example could be that you have AB, 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 right? So in this case, you can just repeat AB 5 times and then you get this correct, this original string, right? Or you can also have something like, let's say B, 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 B. So in this case, you can just repeat this substring of size 1 again 5 times and then you get the original string. Okay. Is the problem clear to everyone? So for this case, you return true. For this case, again, you return true. For this case also, you return true. And let's say if you have something like this. Here, there is no substring by repeating which we can form this string, right? So for this, you will be returning false. Okay, Prakash has an observation that frequency of every character should be multiple of k. That is absolutely correct. But is that sufficient? Is that a condition that is sufficient to solve this problem? Sai Kiran is also saying, okay, let me take another example. What about A, B, B, B? What about this case? Do you return true here or false here? What is the substring by repeating which you get this string? So frequency of all the characters is same. A is appearing 3 times, B is appearing 3 times. Is there any substring by repeating which I can get this original string? No, right? So this is not going to work. reverse the string from half of the string, then make a new string. If it is palindrome, okay, that is a very interesting approach, Rajiv. Let us try that out if it's going to work or not. Okay, so I can have something like, let's say, ABC, ABC, ABC. So you are saying that we should reverse this string from half, right? So first of all, from where should I reverse? There are 1, 2, 3, total 9 characters are there. So either I can reverse from here or maybe I can reverse from here as well, right? So let us reverse the last. If I reverse this part, what is the answer that I'm getting? A, B, C, A. B remains as it is. I get C, B, A, C. This is not a palindrome. If I reverse this complete part, then I get A, B, C, A, and then C, B, A, C, B. Again, this is also not a palindrome, right? Can we do it using 2 pointers? I don't know, Akshat. If you are able to do it, you can just propose your approach. Sliding window, Dikshit Garg. Sliding window, how are you going to use a sliding window? You don't know what is the size of the substring. The substring can be of size 3. This substring can be of size 1. This substring can be of size 2. This substring can be of size of any size, right? Check if repeating pattern as in RobinCarp. Okay, so Tuhin, you will be checking for substrings of each and every sizes, right? LPS using KMP algorithm, yes. Ajay, that is J, that is going to work. But what is the logic behind using that? Find minimum substring and then check. So minimum substring is going to be of length 1. So how are you going to use this? And guys, there can be repetition inside the substring as well. I can have A, B, B, A, and then again A, B, B, A, B, B, A. In this case, I have a substring of length 4, which is A, B, B, A, which is repeating. There is no condition that the repeating substring should have unique characters. You can have repetition inside the substring as well. The difference between two occurrence of character must be equal. Again, Prakash, can you see this? This is violating your observation, right? Check for all the substrings which are having length, that is a factor of original string length. So again, Arun Kumar, you are going to check for each and every possible substring, right? Any substring that can be a contender, you will be checking for that, right? Can we use stack Komal? You can definitely use anything that you want, but the problem has to be solved, right? So you are free to use any data structure. Find the distinct character in the string using map, then use sliding window of size equal to number of distinct character. Okay, so in that case, Dipanshu, if I talk about this example, you will be using a sliding window of size 2 because there are exactly 2 distinct character, right? But if you use a sliding window of size 2, you will get false, whereas the answer should be true because this string of size 4 is repeating. Identify repeating string and push. Azim, that is the question, how to identify the repeating string. You are starting your algorithm from the question itself. Is this problem NP hard? No. This problem has a linear solution. Okay, guys, let us discuss the solution. So if the string is formed by repeating the substrings, what if I join the end to the start? I have AB, AB, AB. Okay. What if I create a circular list? So AB, AB, AB. Right. So if a string of size 2 is repeating, this is my original string AB, AB, AB. If a size 2 is repeating, then from index 2, I will again have the exact same string, right? From here again, AB, AB, AB. I have another string which is exactly the same. From index 4 again, I have exactly the same string of the same length, right? If you just join the end to the start and you create a circular string, and if there is a pattern which is repeating, currently we don't know whether the pattern is repeating or not. But if there is a pattern which is repeating, then you will find the same string again and again in that circular string. We can take another example. Let's say that we have A, B, C, A, B, C, A, B, C. Okay. Now here you can again observe that this is your original string from A to C, right? And again you get same string ABC, 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 right? Starting from index 3. And then you can get another same string starting from this index, ending here, right? So you will be getting multiple copies of the same string inside that circle if you just join the end and start. So you can also assume this thing that let us say that you have a chain, right? If you have a chain, what is a chain? Chain is nothing but this is a sequence of similar type of things, right? You have a ring of gold and you attach another ring of gold to it and you keep attaching, you get a chain, correct? Now if you join these two, correct, then which is the start, which is the end, you don't know, right? You can actually say that this part is my start or this part is my start. All of them are going to give you a chain of the exact same length. Similarly, here you can assume this whole string as a chain. If you join these two, now which is the start, you don't know. From any start, you can get the exact same string of the same length, correct? Now, actually adding the end to the start is going to be difficult and that is going to be hard. What we can do is, we can add the same string. If we add the same string at the end of it, so let us say that I have AB, 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 right? Now if I add the exact same string, append the exact same string after this, so I have made an observation that if there exists such a case that a substring is repeating and then forming the complete string, then in the circular string I will be getting multiple copies of the same string, right? I'm not able to create a circular string, hence I have added this same string, I have appended this string to itself. Okay, now if in this complete string, if I am able to get a copy of the original string, can I say that a pattern is repeating? If I am able to find the occurrence of AB, AB, AB inside this string, can I say that a pattern is repeating? Okay, so I have created this string just by doubling the original string. So this will definitely be searched here and here, right? So we should make sure that we are not searching the original strings. So what we will do is we will try to search in this box. Okay. Now, if in this box, if I am able to identify an occurrence of the original string, can I say that a pattern is going to repeat? Yes, no. Let's take a generalized example. Let us not take specific example. Let's say that I have a string A1, A2, A3, A4, A5, A6. Okay. If this is the string, what I am proposing is, let us append itself to itself. So I will be having A1, A2, A3, A4, A5, A6. And now try to find the occurrence of the original string. The original string is A1, A2, A3, A4, A5, A6. If I directly try to search it, I will definitely find it here, right? Because this is the exact same string. So I will have to make sure that I'm not trying to search in the original string. So I will search in this box. Now, if we are searching in this box and if we get an occurrence, let us assume that I get an occurrence here. What does it mean? If these two are similar, right? In this case, you can see that this is the actual case, right? If you are searching for an occurrence of this string, you get it here. This means that if these two are equal, this means that A3 is equal to A1 and A4 is equal to A2 and A5 is equal to A3 and A6 is equal to A4, right? Because if these two strings are similar, then character-wise character, they are going to be exactly the same, right? So A1 is going to be equal to A5 and A2 is equal to A6. I have written this string here and this string here. Correct? Now I am able to see that A3 is equal to A1, A4 is equal to A2, and A1 is equal to A5, A2 is equal to A6. What does this mean? Let us also join these two. If these two equations are correct, then A3, A4 is going to be equal to A1, A2. Similarly, A5, A6 is going to be equal to A3, A4. Similarly, A1, A2 is going to be equal to A5, A6. Now you can see that these two are equal and these two are equal and these two are also equal. This means that each and every term is same. Now does this make sense? What have we just proved? We have proved that A1, A2 is equal to A3, A4, which is equal to A5, A6, which means that this is a substring which is repeating. Right? Let's take an example of a size 3 substring. Right? So if we have ABC, 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 and okay, let's take a smaller string. Now, if let's say this is the string, first we just append it to itself. So we get ABC, ABC. Now we'll be finding the occurrence of the original string in this new string, and just to make sure that we are not searching in the first occurrence of this string, we are removing the first character and the last character. Okay. Now, if we search this string, where are we going to find it? This string can be found here. ABC, ABC. Correct? Let us write a generalized version also. So this is nothing but A1, A2, A3, A4, A5, A6. And we have appended A1, A2, A3. A1, A2, A3, A4, A5, A6. And now we are searching for A1, A2, A3, A4, A5, A6. We are searching this in this part. Okay. And as per this case, we are finding it after the third character, right? So we are going to find it here. What does this mean? This means that A4 is equal to A1, then A5 is equal to A2, then A6 is equal to A3, then A1 is equal to A4, A2 is equal to A5, and A3 is equal to A6. Okay. Again, if you just combine these two equations, what do you get? You get that A4, A5, A6 is same as A1, A2, A3. Right? This is also showing the same thing, which means that this is a substring which is repeating. Okay. Take example of ABC, BAC. Okay. ABC, BAC. Okay. This is the string which is given. We just append the same string. We append ABC, BAC. Now we remove the first character. We remove the last character. And we try to find the occurrence of ABC, BAC in this. Are we able to find an occurrence here? I can search that A is here, but then B is not there. Then A, B, C is here, B, A. So this string is not being able to find. So I am not able to find the occurrence of this string inside this this given string, right? Which means that if you join this string, if you create a circular string, you are not going to find another occurrence of the same string, which means that there is no such pattern which is repeating. Why to specifically remove first and last character? Okay, so why are we removing the first character? See, this s dash, this is the string s dash. This is created by concatenating the string s and s. This means that you have this string s, you have this string s, and by concatenating them, you have created s dash. Now you are searching for an occurrence of s, correct? If you don't remove any character, don't you think that you will directly find a match here? The first n characters are going to be exactly the same as this string because these two are exactly the same. To make sure that you are not matching it with the original copy here, we are just removing one character. Now similarly, since this is also the exact same string, We don't want S to be matched here with this second copy. So that is why we are removing this character as well. Now what we are proposing is, if you find another occurrence of S inside this part, then that means that this string, if you join the strings end and start, then you will be able to find the occurrence there, which means that there is a pattern which is repeating. Okay. Bhavya Sai, is it clear why we are removing the last and the first character? XXKS creations XX, is it clear now? Santosh, you think about that yourself. If you remove any random character, first of all, what is the purpose of removing the character? Okay. Second thing is, if you remove any random character, does our initial observation holds true? What was the observation? The observation was that if these parts are repeating, then you will be able to find another occurrence of the string inside this circular string. If you remove a random character, right, you break the link. Now these two links are not exactly the same. Right? So first try to understand what is the physical significance of removing the characters. Then you yourself think, this thing that will removing a random character makes sense here. Okay. You always want, what are we trying to emulate here? Right? We want to have a circular string. Right? If you can create a circular string, then we will go with that. Else, just to make sure that we are having a circular string, we are just adding the same string after it. Now this is also representation of the same string in a circular way. Okay. What about just B? Okay, so Agat has another question. What about just B? If let's say the string is B, 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 B. Okay, now what is the first step? Just add the exact same string. Then you can check in this string, are you able to find the original string? Are you able to find? Yes, this string is found here only, right? So you can say that A2 is equal to A1 and A3 is equal to A2 and A4 is equal to A3 and so on, right? So this means that you have got a repeating substring which is of length 1. Okay. Given string is B. Okay. So you are saying that given string is only B, correct? So now for this you can directly check. This is something that you can do on your own, right? You can directly check that the length of the string should at least be 2. Then only a substring will repeat, right? So I will not discuss this. You can add this to your code yourself. Okay.